Okay, so example number 3 features an ice skater. Of course it does, why wouldn't it? Skating around on a large flat ice rink. It tells you at time t is 0, the skate is fixed point O, and it gives you the velocity. It then tells you some more information that at time t 20 the skater is travelling with that velocity. And it tells you that the position vector we're going to call s and the time t seconds. So it asks us to find the acceleration given that it's constant. So this line about constant acceleration just means that we're allowed to use our Suvat formulas. So all I'm going to do is I'm going to write down everything we know. Right, we know that the initial velocity was 2.4 minus 0.6. We know the time is 20, and we know the final velocity at that time is minus 5.6, 3.4. And it asks us to find the acceleration. So again, you can see we've got that ut, the v and the a, so we're going to use our equation that v equals u plus at. So we've got minus 5.6, 3.4 equals 2.4 minus 0.6 plus a, which remember is a vector, times 20. Okay, so then all I'm going to do is I'm going to move over this vector to the other side. So I'm going to subtract each of these from there. So minus 5.6 minus 2.4 is minus 8, and 3.4 minus 0.6 will give you 4. And this is 20a, so now divide by 20 in order to get a. So this will give you minus 0.4, and this will give you positive 0.2. And it's an acceleration, so meters per second squared. Alright, that's part A, just rearranging that v equals u plus at. It then wants an expression for s. So remember, s was the location in terms of t. So that means that t is no longer 20, t is the thing that we're looking to find. So all we have is u, v and a. So we're going to use the equation if we want to find s that relates s. So it's s equals ut plus a half at squared. Remember, we don't know what t is, we're looking for a general expression. That's what it means by expression for s in terms of t. But we can substitute in u and a that we know. So s equals 2.4 minus 0.6 t plus 1/2 minus 0.4, 0.2 t squared. And then all we have to do is neaten up. So any constants we're going to put inside the vectors, and then we're going to add them together. So this is 2.4t up here, minus 0.6t here, and then half each of these values and times them by t squared. So minus 0.2t squared and 0.1t squared. Then we make it a single vector by adding them together, which would be 2.4t minus 0.2t squared and minus 0.6t plus 0.1 t squared. So after time t seconds, this is the location in our vector format of our ice skater. For part C, we're looking at the time at which the skater is directly northeast of O. So for part C, what we should have is that our skater, if we drew a little diagram, if this was the origin, to be northeast, this is north, this is east. So if we just pop them in, to be northeast, that means that we've got an angle here, it's got to be in the middle of the two, has to be 45 degrees. And for us to be the middle of the two, that would tell us that if we think about the components to the side, I'll draw them in here for you. Right, so if we think about this way and this way, these two would have to be equal. So for it to be going between north and east directly, this value here, the I, or the x direction and the y direction would have to be equal to one another. So the x would have to equal the y. So we're going to see if we can set up something. Alright, we've already said from the previous question that that is the location of the skater, and that's the I component and the j component. So for us to be exactly northeast, for that angle to be 45, this part has to equal this part. So all I'm going to do is set up an equation that puts the I component, the x component, equal to the y. If this is the x and this is the y, it tells me that 2.4t minus 0.2t squared equals minus 0.6t plus 0.1t squared. Okay, then what I'm going to do is rearrange it. So this is put everything on the same side where the t squared is positive. So I'll have 0 equals 0.3 t squared minus 3t. Then I'm going to factorise t out. So t 0.3t minus 1. This gives us t is 0 as an answer, but it also gives us t is 1 divided by 0.3, which gives us that t is 3.3 recurring seconds as well. Oh, sorry, I missed a 3. 3 there, which would give us much better. 3 divided by 0.3, which gives us 10. Okay, so we've got 0 and 10 seconds. Obviously the 0 we're going to reject, right? Although these xy's will be equal, they'll both be 0. So that's not northeast, that's at the starting point. Whereas t equals 10 is the answer that we want. It's 10 seconds, which will be exactly northeast. The final part of the question asks us about a second skater, and it gives us her position vector, which is 1.1t minus 6j, relative to O at time t. So the first thing to notice about her is she has no I component at all in part D. So what we're going to do is we're going to take the them and we're going to see if they're equal. So obviously the first thing that we're going to do is see if those j components are ever the same. So if the j components are the same, that will mean that they're at the same height, and they're relative to that. If we know that the j components are the same, we have to check to see if the i components are the same at the same time. So let's look at the j components first. So the j component from our first skater is minus 0.6. So let me just write j components. Right, so she's minus 0.6t plus 0.1 t squared, and our other one is 1.1t minus 6j. Right, she's all j component. There's no I at all. That is all multiplying the j, so she's just moving upwards in that straight line or downwards in that j direction. So then we've got an equation that we need to solve. So we'll rearrange it. It's a quadratic, 0.1 t squared minus 1.7 t plus 6 equal to 0. Doesn't look like that's going to factorise to me, so I'm going to straight away get my quadratic formula out, put it in my polynomial solver in my calculator and see what comes of it. 0.1, 1 minus 1.7 and 6. Okay, so when I solve that, I get two values, very nice. I get t equals 5 or I get t equals 12. Right, so that is when they are on the same, have the same j component. So if I draw a little diagram of that, right, this is like the j component. We could have a situation where skater 1 can be my green one, is up here, and skater 2, which is the second one that's been introduced in part D, could be down here. They would have the same j component, but they certainly wouldn't be intersecting. So what we need to do with those two values is see where they are in the I direction at that point. So if we look at the second skater, we've already said the second skater has no I direction. So we need to check about skater 1, check the I position of skater 1. So the I position when t equals 5 comes from up here still, 2.4 times 5 minus 0.2 times 5 squared. Pop that into our calculator. 2.4 times 5 minus 0.2 times 5 squared. This is 7, right, which is no good. So whilst they have the same j component, the second skater has got an I component of 0, and our first skater, right, has got an I component of 7. So this is no good. It doesn't equal 0, so they're not in the same position. T equals 12, right, we're going to pop that in as well. Same thing, 2.4 times 12 minus 0.2 times 12 squared. And we get this is equal to 0. So that means that they are in exactly the same location. They both have the I component of 0 and they have the same j component, which means that they are going to be in the same position at the same time. The book has very generously decided that would be their meeting. I think if you meet someone in ice skates and you're at the same point at the same time and you're moving with any velocity, I think we call that a collision. So they collide. Hope they're all right. When t is equal to 12. So after 12 seconds, it's all going along nicely, and then they crash into each other. Okay, that's the end of the first lesson. So let me give you some questions for you to do on that. So if you have a little look at exercise 8a. So exercise 8a, and it's going to be question 1. I'm not going to do all of that, we're just going to do a few, so we'll do the odds from there, and then from that point onwards you can have a go at the even questions after question 1 odds. Okay, so they're all going to be different, they're all going to have that element of problem solving, but have a go, follow this one. I know this last one was a tricky example, but hopefully you understood it, and have a go and see how you get on.